Hi everyone, welcome back to Math 256. This is Scott. Let's get started. So the subject of the moment will be section 5.2, in which we are going to figure out how to solve at least some categories of systems of differential equations. So in particular, this is going to be what is called the eigenvalue method for homogeneous systems. Alright, so first off, homogeneous systems. What that means is we have a setup such as the following. So what it means to be a homogeneous system is that we are going to have a system of linear first-order differential equations with no constant term. So a homogeneous system of linear first-order differential equations. So a homogeneous system of linear first-order differential equations, and what I mean by homogeneous here is the same thing as what I meant by homogeneous if we were just talking about a single linear first-order differential equation, namely that there's no constant term and there's no t term. So no constant term is really the important thing about this. So then what it looks like is x1 prime is equal to some coefficient a 1, 1, x1 plus a 1, 2, x2 dot 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 up to a 1n xn. Then x2 prime is equal to a 2, 1. So we've got a system of double indices, just like with matrices, and it's no coincidence. So a 2, 1 times x1 plus a 2, 2 x2 plus dot 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 a 2n xn. And then we'll do some dot dot dots. Xn prime is equal to dot 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 a n1 x1 plus a n2 x2 plus dot 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 and dot 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 and dot 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 going down diagonally here, plus dot 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 going down that way, and then a n n xn. So as you can see, we have a lot of coefficients, a lot of pieces, and a lot of unnecessary writing. So the way we can collapse this into a more efficient way of writing it is as follows. So we can write x as a vector, which equals x1, x2 down to xn, which then means x prime as a vector will be the derivatives x1 prime, x2 prime, dot dot dot, xn prime. We can write A to be the matrix made up of all the little a's, all the coefficients. A11, A12 dot 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 A1n A21 A22 dot 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 A2n dot 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 A N1 dot 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 A N2 diagonal dot 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 also that dot 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 also this dot 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 to make A N N. And then what that gives us is a way to represent this very expression as in fact a matrix product. So then x prime is equal to a x. So if you think about what it means to have a matrix times a vector, it means producing, in fact, this exact system of equations. Now what that means then is that if we're thinking about this in terms of vectors and matrices, then what that means is that the derivative here is in fact the equivalent of doing a linear transformation on the original function, which we can represent with the matrix. So then, differentiating x is the same as multiplying by a. But if we can find eigenvalues and eigenvectors for a, then that gives us a simpler way of actually expressing that very product. But if a has eigenvalue lambda and eigenvector v, then ax is the same as lambda, AV is the same as lambda v. This is by definition. So if you remember what the definition of an eigenvector is, it is a vector such that when you multiply by a, then that is the same as merely multiplying by a constant, which is called an eigenvalue. So what this means then is that a minus lambda I times v is the same as just 0, which means that we can find lambda by setting the determinant of a minus lambda I equal to 0, and solving. If you'll recall, that's what's called the characteristic polynomial and the characteristic equation. And then we can find v by finding let's say non-zero solution, non-trivial solution. Non-zero solution to the system of equations a minus lambda I x equals 0. And then if the eigenspace of A, which you'll recall, which is the subspace, generated by A's eigenvectors, so if the eigenspace of A is of dimension n, then any vector x can be expressed in terms of eigenvectors of A. So what this means is that if we actually can pin down the eigenvectors of A, we can actually express the effect of differentiation by means of a much simpler process. And the long story short here is then so dot 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 after some steps of logic, then the general solution to the system x prime equals ax will have the format. So this is outside of the situation of weirdness. So we'll have the format, I'll say the basic format. X equals, and then what we'll have are our constants C1 and then times e to the lambda 1 t v1 plus c2 e to the lambda 2 t v2 dot 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 up to cn e to the lambda n t vn. Now there are, of course, going to be the usual amounts of exceptions that come up, and the exceptions fall into the usual category of exceptions when it comes to solving polynomial equations. So there are three cases. Distinct real eigenvalues, in which case everything goes great. In which case everything goes well. Second case is complex eigenvalues. As we'll see, this is a little bit harder, but it is still actually within our grasp. So, a bit trickier. But it's very similar. To the approach with second degree. With second degree equations. And then finally, 3, the hardest case, which is the repeated eigenvalues, which is going to be so hard, we'll put it off to another section. And this is too hard for this section. Needs a new section. So in particular, it's section 5.5, I believe. So see section 5.5. Okay. So let's see what to do. So first case, the distinct real eigenvalues. So distinct real eigenvalues. Let's try this one. x1 prime equals 2x1 plus 2x2. x2 prime is equal to x1 plus 3x2. Alright, well, we know how the eigenvalue situation is found from 261 as soon as we have it in the form of a matrix. So 2, 2, 1, 3 times x is what the system really amounts to. Okay, well then, the determinant of A minus lambda I, so I here is the identity matrix in usual Math 261 style. So this is equal to 2 minus lambda, 2, 1, 3 minus lambda. The determinant of all of that, which if you remember, so if it's been a while since you've done Math 261, determinants come from doing this times this minus this times this, and we're supposed to set that equal to 0. So 2 minus lambda times 3 minus lambda, so it's that times that, minus that times that, minus 2 times 1. So then you multiply all that. So this is what's called the characteristic polynomial. So you multiply that all out, and it's going to be a lambda squared. We're going to have minus 2 lambda minus 3 more lambda for a total of minus 5 lambda. We're going to have 2 times 3 is so plus 6 minus 2. So it's going to be lambda squared minus 5 lambda plus 4, and we set that equal to 0. oops, plus 4 equals 0. And then you can factor that, so that's going to be lambda minus 4, lambda minus 1, which gives us lambda minus 4 equals 0, lambda minus 1 equals 0. So lambda equals 4, lambda equals 1. And then what we have to do is take these two cases individually and use those to find the associated eigenvectors. So let's start with the lambda equals 4 situation. So if lambda equals 4, then that means that A minus lambda I would equal the matrix that you would get, which is 2 minus lambda, 2, 1, 3 minus lambda with 4s in place of lambda. So it's going to be negative 2, 2, 1, and then negative 1. So then we just need to augment with zeros. So that way what we've got here is the augmented coefficient matrix negative 2, 2, 1, negative 1 equals 0, 0. So that now what we've got here is a system of equations that are equal to 0, so it's a homogeneous system of equations, and we just need to, that's x1, that's x2, we just need to figure out here what would be a solution to this. So if you take either of these two equations, for example, just this one because it's easier, that gives us x1 plus x2, minus x2 equals 0, which means x1 equals x2, which means that x, which equals x1, x2, will just be two copies of the same thing. So we can set x1 equals x2 equals just 1. So then x will just equal 1, 1. So 1, 1 will be an eigenvector. So v1 will be 1, 1. Similarly, if lambda is the other eigenvalue, if lambda equals 1, then what we will have is the situation A minus lambda I will be 2 minus lambda, 2, 1, 3 minus lambda, where now 1s are going in there, which is going to make 1, 2, 1, 2. And so then we're going to produce the system 1, 2, augment 0, 1, 2, augment 0, and we can just take any of these, and this is going to make x1 plus 2x2 equals 0, which means x1 equals negative 2x2, which means that if I set x2 equals 1, so if I set, and so this x2 is a free variable here, so we can set it equal to whatever we want. So I can set x2 equals 1, and then x1 will equal negative 2. So then that means x is going to be 1, negative 2, the vector, which means that the eigenvector here will be 1, negative 2. And then what that means is that our system has a solution, the general solution, so then the general solution will be x equals, so there's going to be some mystery c1 times e to the lambda 1, which will be 4t, times the eigenvalue, or eigenvector 1, 1, plus c2 e to the 1t, or just t, times the eigenvector 1, negative 2. Now, if I were to actually multiply these out, it would be c1 e to the 4t, c1 e to the 4t, plus c2 e to the t, and then minus 2 times c2 e to the t. And that would be what x1 and x2 would be, which then gives you the solution x1 equals c1 e to the 4t plus c2 e to the t, and x2 is equal to c1 e to the 4t minus 2 c2 e to the t. And then the c1 and c2 we would find using initial conditions if they were given to us. So we would find the c1 and c2 from initial conditions. All right. Let's try that one more time. So that was example A. Now, for example B, we're going to go again, but this time x1 prime will be 9x1 plus 5x2. x2 prime will equal 3x1 plus x2. And so, again, we change it into a matrix, 9, 5, 3, 1, that's x prime times x. And then it's up to us to find eigenvalues, eigenvectors. So, if I do 9 minus lambda, 5, 3, and 1 minus lambda, set that equal to 0, then we'll have the usual 9 minus lambda, 1 minus lambda, minus 5 times 3. So remember how you take determinants of a 2 by 2 matrix. It's A times D minus B times C. And then you multiply these all out, and what do you have? You have lambda squared, you have minus 9, minus 1, so a total of minus 10. Lambda plus 9 minus 15 equals 0. So that's going to be lambda squared minus 10 lambda. No, it's going to be minus 6 equals 0. So this one we can't solve by We can't solve by quite the same means of just factoring it, since this can't be factored. So we're going to have the quadratic formula, for example, or completing the square or something like that. So b will be -10, c will be -6, and that's going to give us lambda equals -b, so it's going to be +10 plus minus square root of b squared, which is going to be 100 minus 4ac, so that's going to be plus 24 divided by 2a, and so that's going to be 10 plus minus the square root of 124. Now 124 is in fact divisible by it is in fact divisible by a perfect square. It's clearly divisible by at least 4, but in fact, if we so if you have a TI-89, you can actually get the clearest version of these by just keeping it in exact mode and doing square root of 124, and it'll actually break it down for you a little bit. So it's going to be 10 plus minus 2 root 31 over 2. And now you can just simplify that slightly to make it 5 plus minus square root of 31. Now, if you want, you could write this as a decimal, or you can leave it in its exact form. Personally, my preference is slightly inclined towards the exact form. This is, after all, a math class, and so that's just sort of the custom of our folk. But anyway, so it's up to you though. So lambda equals 5 plus square root of 31 for one thing, and 5 minus the square root of 31 for another thing. So then we just need to find any non-zero solution to 9 minus 5 plus the square root of 31, and then 5, and then over here 3, and then 1 minus 5 plus the square root of 31. Augment with zeros. So notice that the second time out the gate, we're writing out fewer of the steps, and that's the usual compression of a mathematical technique. All right, and then this is going to become, if we distribute the negative, it's going to be 4 minus root 31, 5, 0, 3, and then -4 minus root 31, 0. Now here you can choose either of these two. And so in particular, let's just say that I take this one. 4 minus root 31 times x1 plus 5 times x2 equals 0. Now, what that means is 4 minus root 31 x1 equals -5 x2. Now you just need any solution to this, so one solution you could get would be just basically swap the coefficients around. If this were equal to that, and if this were equal to that, then it would all work out. So x1 could equal -5, x2 could equal 4 minus root 31. And so That'll give you a v for this one of -5 and 4 minus root 31. Now, think about what will be the same and what will be different if we were to go with lambda equals 5 minus root 31. Everything will be very similar except every root 31 will be opposite. So this is going to be the exact conjugate of the previous ones. This will be conjugate. It's the conjugate of the previous one, which means that v is going to be the exact same thing, just everywhere there is a 31, it'll be opposite. Or root 31, it'll be the opposite. It'll be -5, and it'll be 4 plus root 31. So we can save ourselves a little bit of the aggravation by just recognizing that what will happen as we go down this line will be the exact conjugate of the previous result. And so then that gives us an x, so a solution c1 e to the 5 plus root 31 t times -5 4 minus root 31 plus c2 e to the 5 minus root 31 times t times -5 and 4 plus root 31. Now you can just go ahead and evaluate these as decimals if you want, and it can make your life a little bit easier, but part of the reason why I did it actually this way is that it makes it suggestive for what we're going to end up doing in the case of complex eigenvalues. So this is fine. We can leave it like this. We can leave it in this form. No reason to multiply it out like we did on the previous one unless we have some specific thing that we're hoping to accomplish by doing so. And because of how messy the expressions are here, I don't see any good reason to do that. So now, let's discuss what to do about complex eigenvalues. Alright, so here's the basic idea. So the basic format of solutions is going to rely on the same trick as it did back when we were talking about second order linear differential equations, and in particular what we're going to have is c1 e to the alpha t cosine beta t plus c2 e to the alpha t sine beta t. Now, what we're going to have to do, though, in order to make this actually work out properly, is it's going to be a little bit of a hassle in that we are going to want to approach it this way. So the approach. So the approach is going to be find any complex eigenvector v. Then complex eigenvector v for eigenvalue lambda equals alpha plus beta I. Then multiply out e to the alpha plus beta I times v, which in other words means, according to Euler, with a t up there, which according to Euler's formula means e to the alpha t times cosine beta t plus I sine beta t. And then times the v. And then you are going to collect it into its real parts and its imaginary parts. So multiply this all out. So you're going to have a number here, and then collect it into its real and imaginary parts. Which means, in other words, by imaginary parts, what I mean is the terms that have the factor of I. So the parts that do versus the parts that don't have the factor of I. Factor of I, by I here I mean classic I, the imaginary unit. And then x1, so set x1 to be the real part, and x2 to be the imaginary part. Without the I. Then x, the actual solution x, will be c1 x1 plus c2 x2. All right, so let's give this a try. So it sounds tricky. Is it? Yes. All right. As an example, x1 prime is equal to 2x1 minus 4x2. x2 prime is equal to x1 plus 2x2. Alright, so nothing is different in the way this is laid out from any of the previous ones, and nothing is different about the first steps of our approach. So here we'll just first clarify what the actual matrix that we're talking about here is. So 2, negative 4, 1, and 2 times x. So then a minus lambda I, the determinant of that, we're going to set equal to 0. So a minus lambda I is going to look like 2 minus lambda, negative 4, and then 1, and then 2 minus lambda. And that's supposed to all equal 0. We're taking the determinant. So now that times that is 2 minus lambda times 2 minus lambda. And then plus negative 4 times 1 equals 0. And so then negative lambda makes a lambda squared. And then we're going to have minus 2 lambda minus 2 more lambda, so minus 4 lambda. Then plus 4, and then oops, so this is going to be minus negative, so it's going to be then plus another 4 equals 0. So lambda squared minus 4 lambda plus 8 equals 0. So you can complete the square of this easily or use the quadratic formula. And we'll just go ahead and use the quadratic formula. A is 1, B is negative 4, C is 8. And then what that's going to mean is that lambda equals negative b, so it's going to be positive 4 plus minus square root b squared 16 minus 4ac, so it's going to be minus 32 all divided by 2a, which is going to be 2, so that's going to be 4 plus minus square root of negative 16 all over 2, which gives us 4 plus minus 4i all over 2, which equals 2 plus minus 2i. Okay, now we just take one of these two pieces, either the plus or the minus, as our heart sees fit. It's actually very common to choose the minus, but we'll just stick with the plus. That's what your book says, and we will use that as our framework. So lambda equals 2 plus 2i. And we only need one, and we can get two linearly independent eigenvalue vectors off of that by taking the real and the imaginary parts of this. Okay, so 2 plus lambda I, and that's going to mean when we do a minus lambda I that we're going to be dealing with 2 minus 2 plus 2i, and then negative 4, and then 1, and then 2 minus 2 plus 2i. And then a little bit of cleanup, and we're going to have just a negative 2i and a negative 4. And then down here we're going to have a 1, and we're going to have a negative 2i. And then what we're going to do is we're going to set this. Now we're going to distribute, or we're going to augment this with zeros. So we're going to have negative 2i, negative 4, 0, 1, negative 2i, 0. And now I'm going to choose this one. This one is easier. Look for things like ones, smaller numbers. Those are the kinds of things that make life easier. And then that's going to make an x1 minus 2i x2 equals 0, which means x1 equals 2i x2, which means that if x2 equals 1, then x1 will be 2i. So any solution is what we're looking for here. And in particular, you can just set x2 equal to the easiest thing you can think of, say a 1, and then x1 will follow from that. So then, so one solution will be x1 equals 2i, and x2 equals 1. You can think of it as switching the coefficients around. You can think of it as setting x2 equal to 1 and letting x1 fend for itself. And so what that gives you is an eigenvector of v is equal to 2i1. Now, what that means is if we take e to the 2 plus 2i times t times v, then that's going to be the same as e to the 2t times e to the 2i t times v, which is going to be e to the 2t cosine 2t plus I sine 2t by Euler's formula. And then that is times what we said of 2i and 1. And then that's going to be e to the 2t, which we'll leave out there. But then here what we're going to have is 2i cosine 2t, so I'm just putting it in a more usual order. And then plus 2i times I sine 2t. Downstairs we're going to have 1 times cosine 2t. And then we're going to have plus just 1 times I sine 2t. But the whole point of I is that it is the square root of negative 1, so that means I times I is going to just be negative 1. And so that's going to give us e to the 2t times 2i cosine 2t minus 2 sine t. Sine 2t. And over here we're going to have cosine 2t plus I sine 2t. Which means then we can separate this out into its real and its imaginary parts, which gives us e to the 2t times. And the real part here is going to be the negative 2 sine 2t, and then cosine 2t, plus I. So now this is going to be the imaginary part. 2 cosine 2t and sine 2t. And then what that means is that we are going to have two branches of our solution here. x1 is going to be e to the 2t times negative 2 sine 2t cosine 2t. x2, the other branch of our solution, is going to be from the imaginary part, e to the 2t times 2 cosine 2t sine 2t. And then what that means is that the overall solution in the general solution to this is going to be c1 times this plus c2 times that. The general solution. X is going to equal c1 times e to the 2t times negative 2 sine 2t cosine 2t plus c2 e to the 2t times 2 cosine t. Cosine 2t, I should say. And then sine 2t. Which, if I wanted to break that, if I wanted to put that together a little bit, which in these cases is often going to be good, or maybe not. So I could write it as c1 e to the 2t times negative 2 sine 2t plus c2 e to the 2t times 2 cosine 2t. And down here, c1 e to the 2t cosine 2t plus c2 e to the 2t sine 2t, which we could break into the x1 and x2. So, by the way, the x1s and x2s get recycled a lot here in somewhat contradictory ways. So don't worry about that so much. It's a little confusing, but it's customary amount of confusion. And in fact, I would actually advise you to just leave it in that form. Okay, so this is how we do the general solution. Now let's, for example, try at least one initial value problem. So initial value problems. So the initial value problems, the way these are going to work in these first order systems is that you will just be given initial conditions for each of the variables. So we will be given an initial condition for each variable. So for example, let's take something like x1 prime equals 2x1 minus x2. x2 prime equals 4x1 minus 3x2. And then initial conditions x1 of 0 equals 5, sorry, equals 2. X1 of 0 equals 2, x2 of 0 equals 5. Okay, so these are the initial conditions. Those are the differential equations. Now, away we go. So x prime is equal to 2, negative 1, 4, negative 3 times x the vector. And so now we need to find the lambda. So a minus lambda I, the determinant of that, set that equal to 0. So that's going to mean 2 minus lambda, negative 1, 4, negative 3 minus lambda is equal to 0, which means 2 minus lambda, negative 3 minus lambda, and then plus 4, so minus negative. So it's going to be equals 0. It's going to be lambda squared, and then we're going to have minus 2 plus 3 means plus lambda minus 6 plus 4 equals 0. So lambda squared plus lambda minus 2 equals 0, which gives us then a factorization. Lambda plus 2, lambda minus 1 equals 0, which gives you lambdas of negative 2 and lambda equals 1. So we've got two distinct real eigenvalues here. So now to find the eigenvectors that go with those. So the eigenvector that goes with lambda equals negative 2, we are going to find by taking the matrix 2 minus the eigenvalue we just found, negative 2, and then negative 1, and then 4, and then negative 3 minus negative 2, and then all of that augmented with zeros, and we just need to find any non-zero solution to the system that corresponds with this augmented coefficient matrix. So it's going to be 2 plus 2 is 4, negative 1, and over here we're going to have 4, negative 1. So we just take this one, and that means 4x1 minus 1x2 equals 0. And that means 4x1 equals x2, which then, if we switch the things around, we can have x1 equals 1 and x2 equals 4. Switch the coefficients around, so this is one solution. Any one solution. So that gives us a v of 1, 4. Alright. If lambda, on the other hand, is equal to 1, then we're going to have same thing, 2 minus 1, negative 1, 4, negative 3 minus 1, augment, 0, 0. So that's going to give us 1, negative 1, 0, 4, negative 4, 0. And you just take any of them, the most convenient one. Let's take that one. That's going to be x1 minus x2 equals 0, which means x1 equals x2, which means that we can have x1 equals 1, x2 equals 1 as an example. So that gives us a v for this one of 1, 1. Alright, then what that means is that our general solution is going to look like this. So x is going to equal C1 e to the negative 2t times 1, 4 plus C2 e to the 1t times 1, 1. Now, I know that x1, so at t equals 0, x1 equals, by assumption 2, x2 equals 5. So that means x of 0 is 2, 5. So I can plug in 2, and or I can set equal to 2 and 5. The result of plugging in t equals 0 here. Now, a nice thing about these forms of solutions is t equals 0 means that's going to be an exponent of 0, which means that's just going to be 1, which means we're just going to be talking about C1, 1, 4, plus C2, 1, 1. And you may recognize this whole format from just classic linear algebra. You can solve this by any of the means that you know and love, such as setting it up as an augmented matrix, and row reducing, and doing such things as that. So we could do this, or we could do any other means of solving this. So let's just do this one for a change. Okay, so then if I row reduce this, this would be subtracting 4 times the first row from the second row. Row 2 minus 4 row 1. That's going to be 1, 1, 2, 0, negative 3, and minus 4 times 2 is going to be minus 8, so it's going to be negative 3. And so then this tells us that negative 3 times x2 equals negative 3, which means x2 equals 1, which then x1 plus x2 equals 2. And so I got x1 equals 1 as well. Plug in a 1 there, subtract it from both sides. And so, actually, I should call these all C's. C2, C2, C1, C2, C1, because these are C1, C2. So then, what that means is our general solution is going to be x equals just 1 times e to the negative 2t 1, 4 plus 1 e to the t 1, 1. Which you might, if you wish, rewrite in the form e to the negative 2t plus e to the t and 4 e to the negative 2t plus e to the t. Which you could also separate out into the two variables, all depending on really what you want. Okay, now let's do one more of these examples, but this time with complex eigenvalues. So the one we're going to be doing, this is example B, is going to have x1 prime equals 5x1 minus 4x2, x2 prime equals 5x1 minus 3x2. Initial conditions, x1 of 0 is going to equal 2, x2 of 0 is going to equal 1. Alright, so A is going to equal here 5, negative 4, 5, negative 3. Now, the determinant of A minus lambda I is what we said equal to 0, so that's going to be the determinant of 5 minus lambda, negative 4, 5, negative 3 minus lambda, and that equals 0, which then we multiply out in typical determinant finding fashion, so 5 minus lambda, negative 3 minus lambda, 5 minus lambda, negative 3 minus lambda, and then over here it's going to be negative, it's going to be minus negative 4 times 5, so it's going to be plus 20 equals 0. And so we're going to have a lambda squared, it's going to be minus 5 plus 3, so it's going to be minus 2 lambda, and then minus 15, and then plus 20 equals 0. Which then gives us lambda squared minus 2 lambda, and then plus 5 equals 0. So now we can't use the, we can't factor this, but we can use the quadratic formula. So A equals 1, B equals negative 2, C equals 5, which means lambda equals negative B, so it's 2 plus minus square root of B squared is 4 minus 4ac, so minus 20 all divided by 2a, which is 2, so that's going to be negative 16, which means that it's going to be 4i, which is going to be 2 plus minus 2i, sorry, 1 plus minus 2i. And we will now take one of those, we'll just take the lambda equals 1 plus 2i. And now what we're going to do is we're going to take the 5 minus that, negative 4, 5, and then negative 3 minus that. And we're going to augment some zeros, and we're going to find any one solution that we can. So it's going to be 5 minus 1 is going to be 4 minus 2i minus 4, 5, and this down here is going to be negative 4 minus 2i. And that's going to be 0 and 0. And we can take basically either one of these, whichever is more convenient. So I'll just go ahead and take that one because it's all even. So 4 minus 2i times x1 minus 4 times x2 equals 0. So what that means is 4 minus 2i x1 equals 4x2. I can divide everything by 2, so it's going to be 2 minus I x1 equals 2x2. I can then just switch them around and say x1 equals 2, x2 equals 2 minus I. So then that's going to give me a v of 2 and 2 minus I, which then I'm now going to multiply by e to the lambda t, and that's going to, and then I'm going to collect the real parts and imaginary parts, and those will be the two branches of my solution. So e to the lambda t is the same as e to the 1 plus 2I times t, which is the same as e to the t times e to the 2it, which is in turn the same as e to the t times cosine 2t plus I sine 2t. And so then e to the lambda t times v is going to give us e to the t cosine 2t plus I sine 2t times 2 and then 2 minus I, which on the top is not going to be a problem, but on the bottom is going to be a little awkward. So it's going to be e to the t times 2 cosine 2t plus 2I sine 2t. On the bottom, let's not be heroes here. Cosine 2t plus I sine 2t times 2 minus I e to the t, 2 cosine 2t plus 2I sine 2t. Now down here, multiply those out, and we're going to have 2 cosine 2t minus I cosine 2t plus 2I sine 2t, and then minus I squared sine 2t, but minus I squared is actually just 1. So that's going to be 2 cosine 2t. So I'm just going to now collect the real parts and the imaginary parts. So 2 cosine 2t is the real part at the top. On the bottom, we are going to have 2 cosine 2t and then plus sine 2t and then plus I times, and then here we're going to have 2 sine 2t on the top, and on the bottom we're going to have negative cosine 2t, and then plus 2 sine 2t. And then that gives us our general form of the solution, that x is equal to c1 e to the t 2 cosine 2t, 2 cosine 2t plus sine 2t, plus c2 e to the t times 2 sine 2t negative cosine 2t plus 2 sine 2t. Now I use the initial conditions of x1 and x2. X of 0 is equal to 2 and 1, and I'll use those to solve for the C1 and the C2. So that means 2, 1 is equal to C1 times 1 times 2, 2. So what's going to happen if I plug in 0 for t? 0 for t makes cosine 1 sine 0. Plus c2 times 0, negative 1. Now, I can solve this one the same way I did before, but it's kind of silly because I can just see that 2 equals 2c1, and also 1 is equal to 2c1 minus c2. So c1 equals 1, which then leads us to a 1 equals 2 minus c2, and that leads to c2 also equals 1. So what that means is that finally now I can express my overall solution as x equals 1 e to the t 2 cosine 2t, and then 2 cosine 2t plus sine 2t plus e to the t 2 sine 2t minus cosine 2t plus 2 sine 2t. Oops, sorry. And then, if I wanted to, I could combine those together and have e to the t 2 cosine 2t plus, and I can factor out the e to the t 2 sine 2t, and that would be the first one, and then the second one would be e to the t times 2 cosine 2t plus sine 2t minus cosine 2t plus 2 sine 2t, so I can then combine like terms a little bit. And that's going to then lead me to the conclusion that x is equal to e to the t 2 cosine 2t plus 2 sine 2t e to the t, and then down here that combines with that, so it's just going to make cosine 2t, and then here and here we're going to have plus 3 sine 2t. So those will be the x1 and x2. Alright, well, that is quite enough of that. And I will see you next time for the next episode of Math 256. Till then, bye.